You ever had a program just freeze? I mean, so completely locked up that you have to restart the whole computer? Well, behind that super frustrating moment, there's actually a fascinating and, believe it or not, a really common problem in computer science. So let's dive into this hidden world and get to know one of computing's most stubborn traffic jams, the deadlock.
Now, I know that sounds like the beginning of a bad joke, but the answer really gets to the core of this whole thing. Let's actually start with a super simple, real-world picture to get our heads around this.
Okay, so picture this. A one-lane bridge. Traffic can only flow in one direction at a time. Think of each little spot on the bridge as a resource. Now, what happens when cars try to enter from both ends at the same time and they meet right in the middle? Nobody can go forward, nobody can back up. It is a total, complete standoff. They are stuck.
And yeah, that situation right there, that's exactly what we call a deadlock in the computer world. It's a digital gridlock where two or more programs or processes are just frozen in time, each one waiting for the other to give up something it needs. And just like those cars on the bridge, well, they're going to wait forever. All right, so let's take that idea from the physical world of bridges and cars, and let's see how this whole mess plays out inside your computer, in the world of bits and bytes.
So check out how simple this can be. Let's say we've got two programs. They want to scan a document and then burn it to a CD. Okay, so process A, it successfully grabs the scanner. At pretty much the same time, process B grabs the CD recorder. So far, so good, right? But then, process A needs the CD recorder, which, process B is holding, so A has to wait. And then what happens? Process B decides it needs the scanner, which process A is holding. Now they're both stuck. Permanently. Neither one can move forward. That is a textbook deadlock.
You know, these deadlocks don't just pop up out of nowhere. They're kind of like a perfect storm, actually. You need 4 very specific conditions to happen at the exact same time. And here's the cool part. If you can just break one of these conditions, the whole deadlock can't even form. So first up is something called mutual exclusion. It's a fancy term, but it just means that a resource, like a printer or, a spot on that one-lane bridge, can only be used by one process at a time. You can't share it. This is a super fundamental rule for a lot of computer hardware. Makes sense, right? All right, ingredient number 2 is hold and wait. This is when a program is already holding on to at least one thing, like our process A holding the scanner, while it asks for another resource that's currently being used. It's basically saying, I'm not letting go of what I have, but I need what you have. Third, and this is a big one, we have no preemption. What this means is the operating system can't just jump in and forcibly snatch a resource away from a process. The program has to give it up on its own, voluntarily, usually when it's totally done with its job. You can't just tell a car on the bridge, hey you, back up now. It doesn't work that way. And finally, the last piece of the puzzle, the one that ties this whole mess together, circular wait. This is the standoff itself. You've got process A waiting for something process B has, and at the same time, process B is waiting for something process A has. It creates this perfect, unbreakable circle of waiting. You need all 4 of these things to get that gridlock.
Okay, I know this all sounds a little abstract, and that's exactly why computer scientists came up with a really great way to actually see these situations. It's called a resource allocation graph, and it's basically just a map of who has what and who wants what.
Let's look at a healthy system first, just to get our bearings. So on this graph, the circles are processes, the programs, and the squares are the resources. An arrow going from a resource to a process means the process is holding it. An arrow from a process to a resource means it's waiting for it. See? Everything's flowing along nicely. There are no closed loops. This system is working perfectly. But now, look at this one. A new request gets made and bam, we have a cycle. Just follow the arrows. Process P1 is waiting for resource R1, which is held by P2, and P2 is waiting for R2, which is held by P1. This is a perfect picture of that circular wait condition we were just talking about. When you see a cycle like this on the graph, you are looking at a digital traffic jam.
Okay, so this is the really crucial thing to get here. Seeing a cycle in the graph is a necessary ingredient for a deadlock, but it's not always a guarantee. Here's why. If a resource has multiple copies, let's say you have 2 identical printers, one process might be able to just grab the second printer and break that cycle. But if there's only one of each resource in that cycle, then a deadlock is absolutely 100% going to happen.
All right, so we get what a deadlock is, we know the 4 conditions, and we can even spot one on a graph. So the next logical question is, what can we do about them? How do the people who design our operating systems actually handle this problem?
So, broadly speaking, there are three main ways to go. First, you've got prevention. That's where you design the system from the ground up to make it totally impossible for one of those four conditions to ever happen. Then there's avoidance, which is kind of like a GPS for your computer, always looking ahead and steering clear of potential traffic jams. And finally, there's detection and recovery. This is basically letting the crash happen and then calling a tow truck to clean up the mess afterwards.
Let's dig into that avoidance idea for a second. The whole goal is to keep the system in what's called a safe state. A safe state just means there's always at least one path forward where every program can finish its job without getting stuck. An unsafe state doesn't mean you have a deadlock, but it means you could get one. So, these avoidance algorithms check every single request for a resource to make sure that saying yes won't push the system into that danger zone.
So you have these really smart, really elegant solutions: prevention, avoidance, detection. But what do most of the operating systems that you and I use every single day actually do? The answer, honestly, is pretty shocking. It's kind of wild.
That's right. The most common solution, used by the biggest systems out there, is to just ignore the problem entirely. It's basically a philosophy of blissful ignorance. And yeah, this approach has a famous name. It's called the ostrich algorithm. You know, stick your head in the sand and pretend there's no danger. So why? Why on earth would they do this? Well, the thinking goes like this. Putting in all that fancy code for prevention or avoidance costs a lot of processing power. It can actually slow the whole system down. And since real, true deadlocks are actually pretty rare on modern computers, it's often just more efficient to bet that they won't happen. And this brings us right back to where we started. The trade-off for all that speed and simplicity is that when a deadlock does manage to sneak through, the system has zero tools to fix it. The only solution is the one we all know and, well, the one we know, turning it off and on again. That's you, the user. You become the recovery mechanism.
So this leaves us with a really fascinating thought, doesn't it? In this incredibly complex world of computer science, one of the most practical solutions to a really tricky problem was to just ignore it. It really makes you wonder, what other complex problems, maybe in technology or maybe even in life, have a similarly counterintuitive just ignore it solution? I hope you enjoyed this deep dive into the weird world of deadlocks. If you want to keep exploring fascinating ideas like this one, make sure you like, share, and subscribe to Tech Talk 101. Thanks so much for watching.